this is the whole purpose of this meeting is to do things that Martin Gardner appreciates or would appreciate. And I know he's going to really like what Eleftherios is going to show us. So I'd like to show it to you in the context of monohedra, polyhedra with congruent faces, combinatorial structure of a regular polyhedron. Those of you who've been here, I've been here 6 times, and 4 of my talks were about monohedra. But what I want to talk about today is different. I want to talk about coffee house mathematics. Okay? In Providence, Rhode Island, 7 Stars is a place where a lot of people hang out on the east side. And we share stories and learn new things about each other. Eleftherios Pavlides, over here to the right, is a regular, and so am I. And I couldn't pass up the fact that his coffee table had models on it, and models that changed and shifted. So in particular, one of the models that he looked at really surprised me because, well, first of all, you'll see it, the real thing. But if you take the coordinates of these 3 faces here, you can see that they are forming a dodecahedron. Well, hexagons, but these are only 3 of the 12 units that fit. But it's not the standard thing. Now, as I said, so I wanted to figure out what was happening. Because if we go back on it, it turns out that the angles are not all the same. In fact, the edges aren't all the same. The bottom edge of the green one is shorter than the other 4, and the top one was a right angle. Okay? So I was very interested in right-angled figures, so I sat down, and this is the actual napkin that we use to do the work. And not the first time, but the second time, this is June 1st, 2015, that tilde-gnostic monododecahedron. You can get great names when you put these things together. In any case, monohedra are things I talked about before. In G4G12, I produced this thing made out of 20 congruent right triangles. Square root of 7 was the square root. Last time, square root of 11 was a little harder, but I produced a model which I actually have here, although I wasn't able to show it at the end of my last one. I'm holding it up in the air. You can see it later. And it's, even though it's made of 20 right triangles that are congruent, when you put it together, the abstract metric doesn't have the same faces as the ones you started with. I explained that the last time I talked, so I'm not going to talk about it again. And if you want to see this thing, you can come up and see it afterward. But I want to get back to the fact that the regular dodecahedron, of course, has equal angles. And this is taken from the wiki that you can watch. If you move it, you can see that this thing is actually a sequence which starts with the regular dodecahedron and moves up to the rhombic pyrotohedron. It's just the rhombic dodecahedron. But then we move forward. We get a right-angled dodecahedron in between by intermediate value property. So from the 1, you go to the right-angled one, then to the regular dodecahedron, which we all know a little bit too commonly. And at the bottom, you get a subdivided cube, which is also a dodecahedron, if you think about the fact that each of these subdivided rectangles has 5 sides. Right? So the thing that surprised me is that working with Eleftherios, we figured out why this new monohedron was really interesting. But what surprised me is he continued to work with his elasticity figure and produced at the end something which is also familiar from an earlier time here at Gathering for Gardner, when I talked about Dali and his interest in the 4th dimension. Well, here, for example, is the model from my thesis of the unfolded hypercube. This is the one Dali liked the most, and said when he saw it, I may have this. It wasn't exactly a question. And he wanted to use it. And in fact, if you go to the museum in Spain, you'll see it right now. But indeed, all these things show up on the work of Eleftherios Pavlides. And my gift to our group is to introduce a new member of our group, Eleftherios Pavlides.
So this is the ABC and the AB. This is actually Esser's solution to the problem. He did it only with the ABC, and that's mine when you go back and forth between the two. I call it dactylognosis because it comes from dactyl and gnosis, so it all comes from the fingers, and then the brain interprets later on. Paper is one of the materials, and Bauhaus, they believed material dictates form. So Louis Kahn asked the brick what you like, and said, I like an arch. I asked paper what you like, and said, I like octahedron. I discovered this little pyramid, and then by weaving them, 6 of them, triangles, it turns out others had found the same structure and named it different things. So Robert Neal called it 6-fold ornament. Kiruhiko Kasahara came from origami, skeletal octahedron. I called it paper diamond because it was so hard and 6 pieces of paper. So because calling it diamond, I was stuck with the problem of how does the crystal grow. So I found different ways of growing the crystal. And actually, you can see an actual diamond and the paper version of it. And one of the way of growing the crystal required this 2 square with this folding, these creases. So when I put a slit, and I did the slit just because you could, with no intention, it made 6 crosses of squares that were woven by analogy to the diamond with the triangles. And it took me at least a couple of years before I realized this flaccid figure was not worth throwing around, but by flipping it inside out, you get this icosahedron. I was very surprised, that has this property of going back and forth. And the icosahedron, it's called Elastegrities. So this is a tensegrity. It's made with struts. This is the Elastegrities by analogy, which is made with rigid, it has elastic hinges instead of nodal connection. And you can make, a matrix of them, close packing, which means everything I'll show you, you can imagine the matrix shape shifting. So the first transformation is the 12-vertex structure that happens by collapsing the corners of the cube, the rectangular tetrahedra, and then by folding down, you can fold it into these squares in 3 directions. Tom's hypercube does that, and by pivoting up the triangle, you turn it into a cube. So you get the 3rd Platonic. This cube gyrates back and forth, becoming flat. And then when you pivot up from the cube, through trig, I figured out that, in fact, it was a real flat pentagon. And then Tom generalized it with his analytic geometry. And then you can actually make it regular and everything in between. I did the regular, but then Tom suggested the others, and you could do it through folding. And in the other direction, you can take this corner of the cube and open it up and make a corner of squares instead of corner of triangles, and then pivot these in, and you get a stellated octahedron that becomes a real octahedron if you push them all the way down. And if you pull them up, you get a tetrahedron. And if you think that's too suggestive, you can keep folding it to make it more explicit tetrahedral. And finally, doing all this, you put all these new creases on the paper, and you end up doing a fractal. Maybe I should show you this one. So when we started, this is the piece of paper that gives rise to the original Elastegrities, the one that's like an icosahedron, which is equivalent to the 6 strat. If you make the fractal of it, then you get this, which is equivalent to the 12 strat tensegrity. And I believe, so if you want, I have a couple of minutes, so how am I doing?
Yes.
So this is the hypercube, which by opening up these openings and straightening them, so this becomes that. That's how you get from here to there. And I brought a puzzle for you. I have a stack of them. You can take it and see if you can fold your own. And this is the presentation. This is the summary of all the shape-shifting. And this is returning back in Providence in the cafe. 7 stars, highly recommended. Thank you.
Thank you very much.